talk about the standard model of physics. Before I get there, actually, how many of you are programmers here? Cool. How many of you are machine learning engineers? Got some. Cool. How many of you are into physics or know something about dark matter? Yay. Okay, cool. Alright, so we're going to talk about the standard model of physics. Then we're going to look into what the Large Hadron Collider does. Then we're going to talk about some machine learning challenges in particle physics specifically. And then we're going to talk about looking for dark matter in the LHC datasets. And then we're going to do particle identification. We're going to train some neural networks. And then I will tell you guys how you can do all of what I talked about today. And I really hope that you actually get into it. So you can find all of the data from CERN is actually open source. And you can just go to this URL, and I will put out my site so you can have this URL. But you can take the detector, which if none of this makes sense to you, that's okay. It makes sense to you after the talk. There's like 4 detectors that CERN has, and all of their data is available here. You can click on any of them, and just click on download, and then start analyzing it. It's like pretty straightforward. So, with that out of the way, first thing we're going to talk about is the standard model. Now, it looks complicated, but it's not. The standard model describes what the universe is made of and how it holds everything together. It has 2 major tenets. Everything is made up of fundamental particles, and they interact with each other through exchanging particles that represent force, which are these guys right here. So everything that we see, you, me, galaxies, space, everything is made of 3 things: up quarks, down quarks, and electrons. I actually was surprised that protons and neutrons are not fundamental particles, which is what I learned when I was in high school. Apparently, protons are made of 2 up quarks and 1 down quark, and neutrons are made of 2 down quarks and 1 up quark. Is this sound okay? Okay, cool. This is a better representation of the standard model. So basically, it's broken down into 2 things: fermions and bosons. Fermions are fundamental building blocks of matter, and bosons are fundamental building blocks of force. There's 2 kinds of fermions, and I'm going to use Harry Potter analogies to make this easier. So, how many of you are Harry Potter fans? Okay, next time I'm going to use Game of Thrones analogies. But for now, so quarks are these guys right here. The most common ones are up and down quarks. Everything else decays back into up and down quarks. So they only exist for a little bit of time, and then they pass force particles and other particles and basically turn into these guys. So quarks are like Harry, Ron, and Hermione. They only move in groups. Their charge is not a whole charge. They have like fractional charges. So that's why they need to exist with other quarks. So that's why like protons are made of 2 up quarks and 1 down quark. And Harry, Ron, and Hermione, like they always move together. They're not very good independently. And the next part are the leptons. These are more like Luna good. They kind of do their own thing. They have a whole charge. They don't need other leptons to exist, and they walk around independently. Bosons are the fundamental particles of forces. There's 2 kinds of bosons: the strong force and the weak force. Now, strong force is kind of like Dumbledore. The force itself is very strong, but the range of the force is tiny. So, like Dumbledore has a very strong influence on Dumbledore's army and Hogwarts, but apart from that, not that much. Whereas the weak forces are more like Fudge. He's the Minister of Magic. He kind of runs the whole wizarding world, but like his influence is not that strong on any one particular person. So these work on long ranges, but at 1 million times the scale of strong forces. The Higgs boson, which we all heard about a lot, is weak force, and that actually came about because there was mass that was unaccounted for, and the scientists predicted that something of that nature does exist, and then the LHC was able to detect it first in 2012. And yeah, these are also responsible for radioactive decay. Oh, let's look at the Large Hadron Collider now. So this is what it looks like. As you can see, the scale is crazy. It's made up of 4 different detectors. This is what the tunnels look like right here. It's a 16-mile long tunnel. What it does is it takes hydrogen atoms and takes out protons out of them, and then kind of accelerates these proton bunches in this area, and it smashes them into each other, and these protons then decay into some of the particles that we learned about earlier. There's 40 million bunch collisions per second, 10 petabytes of data is collected every year, it's crazy. And then these individual detectors are kind of like big cameras that are taking a picture of all the particles, the decayed particles that are passing through them. And these detectors measure the energy and momentum, which we will see why it's important soon. I'm going to show you a quick video so you get a better sense of the LHC. Sorry, the sound.
That's good, it works.
So these are the different detectors. You get the idea.
Yeah, great music.
I know. All talk should have background music. Cool. So the main takeaway here is that different particles leave different tracks on different detectors. You will get bored of this picture by the time I'm done with this talk, I'm sorry, but so here you can see photons only leave tracks in the electromagnetic calorimeter. The muons make it all the way to the muon chambers and don't leave any tracks here, and this is kind of how we're able to detect these particles by reconstructing their paths. Cool. One last thing I want to show you before we move into the machine learning part is this guy right here. So you can actually, this is exactly the output of all the detectors that we just saw. For example, this is the last detector that is lighted up by muons, and then different detectors light up, different particles light up different detectors. And then you can kind of zoom through it like a particle, let the particle light, and see what it might feel like. Alright, cool. So you can explore it again. I'll have a link in my slides. Cool. Alright, machine learning time. These are the main problems that, the main machine learning problems in particle physics. A lot of them are similar to regular machine learning problems, which is like, there's a ton of data, we need to process it really fast. Most of the data that the LHC produces is actually deleted. They have some things called triggers, which decide what data to keep, and everything else is just kind of thrown away. Anomaly detection is a problem that is every machine learning sphere has that problem. So basically, your data is going to be dirty. You need to figure out what are anomalies and delete them. Precise and fast particle tracking is also hard because, like, essentially you're taking you're taking pictures of the particles by measuring a bunch of numbers, and then you're reconstructing the paths, so you need to make sure that's precise. Another cool thing is you can use Bayesian optimization. Instead of taking all the pictures of all the particles, you take them at certain intervals, and using Bayesian optimization, you figure out where the particle is going to be. So that's kind of cool. The thing we'll be focusing on is particle identification. And we move to searching for dark matter, which is why you guys came here tonight. So what is dark matter? Does anyone know what dark matter is? Anyone have any theories before I get into that?
It's what holds together the galaxies, right?
Yes.
Yeah.
You know stuff. What about you?
Okay, it doesn't interact with light.
Yes.
It's because it's dark matter.
Yes.
But it affects gravity force and it like bends.
Exactly. Okay.
Right.
Yeah. Anyone else?
I don't think anyone really knows.
Exactly. So maybe the three of you, you got what I'm going to say in the next slide, so shall so 85% of the gravity in the universe is actually unaccounted for. So if you add up all the galaxies, the stars, us, everything, like the mass is only enough for to justify 15%. And if that's all that existed, the galaxies would move farther apart. So there is something that's, producing this gravity. The problem is calling it a dark matter is a misnomer because it's not actually matter. Like it could be, couldn't be, we don't know. We just know that it has some sort of gravitational pull. So we might as well call it thread because thread has as much to do with dark matter as dark matter does. So what do we know for sure? Like you guys said, we know there is something. We know it interacts with gravity. We know it doesn't have any effect on light because it doesn't emit light or reflect light. We also know that there's a lot of it. And it probably has mass because mass and gravity go together, but we don't know for sure. So we don't know a lot. There's a lot of theories about dark matter. The one we'll be focusing on is the WIMP theory. WIMPs are weakly interacting massive particles. So these guys have weaker forces than the weak forces that we saw before, like the W bosons and the Z bosons. These have orders of magnitude lesser force, and they don't interact with other matter, which is why it's hard to actually detect them. And they don't absorb light either, which is why they're good candidates for dark matter. The main challenge here is like we don't know what we're looking for, so it's hard to set up experiments because if you don't know what you're looking for, that's why a lot of experiments have failed in detecting dark matter because the goal is not defined. Also, you can't observe dark matter directly, so you have because it disintegrates or it interacts with particles, and then you can only observe its effect by measuring its effect on the particles that we can actually see. So it's not a direct observation, it's an indirect observation of dark matter. Alright, with that, let's use the machine learning. We'll be doing two things here. The first step is, this is what the output from the detectors looks like. It's ridiculous. This is made up of like 10 billion base tracks, out of which only 10 million are actually useful right here. So the first thing we'll do is eliminate the background noise from the base tracks, and then out of all these electromagnetic showers, we're going to detect which ones are neutrino showers and which ones are dark matter interactions. So neutrinos produce similar showers to dark matter, which is why, and again, this is all hypothesized, but this is the hypothesis we're working with, and so this makes it hard. The difference is the energy angle correlation is different between neutrinos and dark matter. So that's what we're looking for. The data set we're working with has 15 million base tracks. You can see the XYZ coordinates of the tracks. You can see the angles from the origin, but that's actually not available for all data sets. And then there's this thing which tells you whether it's a signal or not. So that's the data we're working with. We also make some additional features, which is we calculate the angle of the base track from the plane. We calculate the projection of the base track on the plane. And the distance is from the origin, but again, the origin is not available in all data sets. The key thing here that we should remember is signals actually have a predefined geometric structure because they're coming from particles and then either disintegrating into particles, which in which case they still have a structure, or just moving through the detectors. Noise is just random, so here you can see this is kind of noise, it's like random. And like this is noise, even this guy is kind of like noise. Everything else has structure. So that helps us distinguish, so it helps us go from here to here. Alright, so I want to stand right, I don't want to get too into the weeds, but all you need to remember from here is base tracks are parallel to each other, and we only see chunks of the tracks of particles. So this bit is all we see, and then we see this bit. So what you're trying to do is figure out, given you see this is the angle of one base track, and this is the angle of the other base track, you're trying to project this back into the previous base track to figure out if it's actually random noise or if it's like part of a track. And this code kind of adds neighbors and adds that information back into the data set. All of this code is available. I'll show you where to find this code, so don't worry about that. Here we're training the neural network. So basically what we're doing is removing information about the actual signal, because we don't want to give our model the answers. We remove that, we normalize our data, so every feature has similar effect on the data, because they're all at the same scale. Our neural network has multiple layers. Basically, these bunches are adding new layers of the neural network, and then you specify what you're optimizing for. You're optimizing for binary cross-entropy because we're detecting signal, no signal is a binary problem. And then these are just more parameters of the neural network. The only interesting thing is you want to stop your network when the loss has been reducing. If the loss is reducing and then it starts rising, this model was better than the final model, so you want to take this one. So you want to stop training if the loss starts going up. Here we train the model and then we make some predictions. What it predicts is probabilities for each row of it being signal. So higher is better. So here we're 54% confident that this is a signal. This is the same code, but we're training a boosting model. The only thing you need to know about boosting models is they train multiple models, and take all of their outputs into consideration. So for example, if I have a test, I take it, and all the answers I get wrong, I take to 10 years for that, and like he answers sometimes, other people answer it, and then at the end you have a better model than if I answered it alone. So that's what boosting trees do. There's a bunch of boosting trees. XGBoost is pretty good, but CatBoost and like GBM are newer and better, so I would recommend using them instead. So we've solved this problem. Cool. Now our goal is to go from the data about signals to figuring out which ones are dark matter tracks and which ones are neutrino tracks. So for that, we're going to be doing something called clustering. There's multiple algorithms to do clustering. DPScan is a density-based clustering algorithm. So essentially what it does is it takes all the data points that are closer to each other and gives them one class, and that's how it classifies everything. K-means is a centroid-based clustering model that does better in our situation. If you want to know about these, you can talk to me later and I can get more into the theory of these. But for our case, Euclidean distances don't matter. This is what these can measure, so we're just going to train a K-means. So K-means is pretty simple. The thing is, you have to tell it how many clusters beforehand. It doesn't know how to detect that. So we train K-means with a bunch of different clusters, and we see that the loss kind of flattens out at 6. So then we pick 6 clusters to train on. Machine learning is essentially just trying things, throwing shit at the wall and seeing what works. Like, nobody knows what they're doing, trust me. The more people I talk to, the more I'm like, what the hell? This is your job, you get paid for this? How much do you get paid for this again? But, so we train our teammates with 6 clusters. It gives us labels for each cluster. We put them in a data set. Here you can see, voila. The blue ones are possible dark matter interactions. Everything else is neutrinos. So now you guys can detect dark matter. Cool. The other thing I want to talk about is SHIP. SHIP is an experiment built specifically for dark matter detection. So basically, right now we're working with data that was collected from detectors that exist already and were not meant for dark matter detection, but they kind of work for dark matter. But SHIP is specifically built for electromagnetic sharp detections, amongst dark matter being one of them. It's going to be launched in 2025, and I hope you guys will play with the data set with me when it comes out. Cool. Done with that. Particle identification. How are we doing? Quick question. Everyone alive? Cool. I'm sorry again. We're going through the theory for like particle physics here, LHC, and machine learning. It's like, I don't know why I picked this topic, but we're here. Cool. So here, this is going to be way simpler. Our goal is to detect the particles from that were like basically take the data set collected from all the different detectors, Alice, Rich, the 4 ones that you saw, and take the inputs and then figure out what the particle was. We have 5 options: electrons, protons, kaons, pions, and muons. And then anything we can detect we just call the ghost particle. So we have technically 6 outputs and inputs from 5 different detectors. This is what the inside of the detector looks like. I don't envy the job of the person who had to design it. Cool. Okay, I'm going to get into the weeds a little bit more because I feel like this is important. So we know that the momentum and energy in any system is conserved. So we use that principle, and if we know the energy, the momentum, and the speed of anything, we can get the mass. This is Einstein's EMC square equation, the full version of that. So basically what we do is, if we know the energy, the momentum, the speed, the mass of the final particles from the readings of the detector, and we can construct the mother particles from that. So for instance here, if we know the energies of all these tiny little like branches, we can construct what the mother particle was, and in this case it's the electron. So that's the theory behind what we're doing here. We're going to again train a neural network and a boosting model. What you want to do is train a few different kinds of models because you don't know what the underlying structure of your data is going to be. So you always want to train a linear model, a boosting model, which is basically essentially a decision tree, and also a neural net because they work differently for different kinds of data. And then you can figure out which one works best for your problem, and then you can try more algorithms of that kind. If you want to talk more about machine learning, I'm happy to nerd out after the talk. This is what the data set looks like. Now, there's 50 features. You get a taste of them here. They're all numerical. There's both features that we measure directly from the detectors and the ones we derive from the detectors. So, for example, like in the last example, we got the base track and the angle from the data we had. There's much more of that going on here. And then, basically, I'm going to teach you machine learning in like 5 minutes right now. All that you have to do. First step, you have your training data, right? You want to set aside a little bit of it, 10%, like depends on the size of your data set, but like 10 to 20% of it you set aside, and you measure the output of your neural network on your test data set, also called validation data set. So here we're splitting our training set into 90% goes into training and 10% into validation. We train, the next step is to define your classifier. We pass it some parameters, and then we have our classifier right here. We fit the classifier to our training data. So we pass the features and what we're trying to predict, which is a class. And then we just make some predictions. We pass our validation data as features, and then we get some predictions. Then we measure the loss. These are the actual values, and this is what your neural net or your boosting algorithm predicted. This is basically machine learning. Define a classifier, fit a classifier, make predictions, measure loss. This is actually also not machine learning. This is the cherry. On the top, most of the time you spend doing feature engineering, which is converting the output of the data set into these, and then like doing a lot of other stuff that is not at all interesting. I mean, to me it is, but to most people it's not. But machine learning itself is just this, honestly. I don't know why we get paid so much, but we should not be getting paid so much. Same thing with neural networks. I'm going to teach you how to build a neural network now. Same principle. Define the kind of layer. So basically, these are, as we talked about, different kinds of layers. Activation functions, what they do is take the output of the layer and convert it into probabilities. So basically, define each layer, figure out, tell it what you're trying to optimize for. In this case, we're going for categorical loss, not binary, because we have multiple classes that we're trying to predict, which is our 5 particle types. We pass our model, our training data set, we fit it, we get some probabilities, measure loss, done. These are the ROC curves, which basically let you plot the errors that you want is committed. The ideal shape of this graph should be, following the axis, so that way and this way. So you want to go like that, and then you want to go come here. So these are the errors. And you measure the area under the curve. So as you can see, the nuance are easily detectable because they, all you have to see is if they make it to the muon chamber, so they're slightly easier to detect. Other things are harder. But the eta boost performs better because the curves are more like the ideal shape of the graph that we're looking for. This is another lesson. Neural networks, you hear a lot about them. They're not useful. They're useful. They're not the only thing that's useful in most cases. Unless you're doing images or like working with reinforcement learning, they try everything. For me, boosting algorithms almost always outperform neural networks. I was going to tell a story. Probably can't tell that here, but basically, trust me, people in the industry, they don't like neural networks as much as the rest of us do. For most problems. Alright, so now it's your turn. I'm not going to ask all of you to pull out your laptops, but I will tell you how you can do all of what I did right now. So, Google bought Kaggle. Great, I'm a part of Google. So, Kaggle is essentially a platform for machine learning engineers. It's a platform for competitive data science. There's competitions running, so you can pick a competition and join it. What the things? Ooh, this is not a good one. I actually can't crash. Let's take this. So this is what a competition looks like. You see a little bit of context about what they want you to do. You see the metric that they're measuring you on, which is one of the most important things. This is what you're trying to optimize. Some competitions have tutorials, most don't. Here you can see a little bit of information about the data you've got. You can download the files here. There's a CLI. Like you can get it through your command line. This is really cool. If you want to get into machine learning, I would say click on a competition, click on kernels, and then you can see the code that the people who are best in machine learning across the world are submitting. And what you want to do is, instead of flatness, you want to do it by best score. So these are the best performing models, and then just go through that code. It's like, and like you learn so much, I'm not even kidding. The cool thing is you can run the code in this environment, which some people don't like, but it's good for explaining your code as you write it and sharing with people. You can see the leaderboard. I'm on here somewhere, right there. This is not what I picked this competition. And so if you want to get the code for the dark matter for detecting dark matter and detecting particle physics that we just went through, you can just search literally for searching for dark matter. Please show up here. And then it'll take you to this kernel, and then you can go through it. What you can do is you can fork it. I'm logged in from my account, so it says edit, but it'll say fork here, and then you can just play with it and impress your friends if that's what they're into. And